Right, so let's start. Thank you for the presentation, Chris. Like you said, I'm Francois Turcotte, product manager for the EATON SMP Gateway. Today, we want to present one use case on when we're using the CODESYS application. And so far, we've been using CODESYS for a very long time into this platform. And I would say this is kind of the basic engine we use for all of our automation we want to do, any advanced automation, because we have a basic module into the platform where we can use just small basic logic. But if our customer wants to do more advanced application, they can use the CODESYS module, build their own script, and automate some application. So let's first talk what's the let's see what's the agenda we're going to cover in this presentation. So first, what's the SMP gateway, how we implement the CODESYS, and also an example of the CODESYS application, which is called feeder restoration, and it's going to be presented by Reza, which is not there yet, but should come very soon. So first, what's the SMP gateway and where we're coming from? We are already part of what we call substation automation, which is a market where people want to evolve in terms of technology in their substation. So they want to have access to multiple devices in a substation. They want to access them remotely. They want to access them securely. So what we offer is a box that allows them to separate their network and just restrict access to those IDs communicating directly in the substation. So the SMP gateway can provide that layer of security where people will just need to configure it and have a single point of access to the remote field. So we provide a firewall. There's multiple different things that we offer into the same box. One of them for sure is CODESYS, but also we offer a lot of things like protocol translator, protocol communication. If you want to, I don't know, the NP6150, all of those standard protocol we support. It can have an HMI also. So a lot of things that is available into the single box. So that's where we're coming from. So in the past, people were just trying to access device remotely through different paths with serial, TCP, any type of communication that was kind of a mess, as you can see, like a spaghetti right there on the left. But the evolution over the maybe the 10, 15 years has been where people want to separate those two layers and have the SMP gateway or maybe another type of RTUs that is accessible and can interact directly from a client perspective. For example, SCADA, EMS, DMS. If there's any other parties that wants to access data from the substation, they can now directly connect to the SMP or an RTU to gather those information. So that's really the goal, is to separate and secure this part of what is critical, what they call a critical asset into their substation. And that's why most people use an RTU or that type of smart device to comply to what we call NERC SIP in North America. where they can comply to a standard made by the USA, but what, let's say, Canada and Mexico, they also have to comply if they want to exchange electricity and if they want to connect to the grid. So what's the architecture on the SMP gateway? So that's just a very simplistic representation of what's inside the SMP gateway and how we interact between all of the module. So first thing is I discuss about is the implementation of masters, and what we call master and slave, which is a master is a module we use to communicate and pull information from an IDs in the substation. So master can interact with an IDs in TCP. It can interact with RS-232. So different type of media or communication you can do with a master to collect information from the field. That comes in the middle, where you can see that real-time data exchange is the middle, or I would say the centerpiece of all the communication between all the module in the SMP gateway. Well, all the values gathered by a master is then sent to that layer and transformed to just as a point. We call a point is just a value, a time tag, and a quality. So that's really just three simple value that each points represent in the system. Because the only thing, or I would say the main thing that this device does is that it concentrates all of these value or tags and translate them from one protocol to another, or it send it to an HMI. It's really just a big box that manage tag value or point value for representation. So for example, if you take masters, pull information, send it to the real-time data exchange, or we call it RTDX, and send it back to a slave, which is you can see it as a server, and send that information to another company. For example, in Canada, we have a few utilities like Hydro-Quebec, Hydro One, Manitoba Hydro, all of those company or utilities that wants to receive those information from the field. So that's where it's coming from. You see the CODESYS PLC is right there, and it's gonna interact directly with what we call the RTDX, or the real-time data exchange, to receive point information and being able to send a command to that layer. So the CODESYS can then, I don't know, if he wants to do any processing on a point that is received from an IED from the field, we could just implement that logic into the CODESYS, where, let's say I want to operate a breaker if I receive a status value from another device. So I receive an input from one device, I treat it here, and I can send a command to that other device to operate if it's needed. So that's kind of logic, very fast logic that we're trying to implement in CODESYS, and that's what most of our customers use. Yeah, very simplistic. This example, they will probably use what we call the automation function to do that, but that's kind of the basic what people trying to achieve with a CODESYS PLC. We have other customer that wants to build a statistics. They just want to compile statistics from device. For example, wind farm project in Quebec, Canada. There, what this CODESYS engine is doing is that it's gathering statistics every 10 minutes on each of those masters and just compile them, and at the end send them back to Hydro-Quebec and saying, okay, here's my statistics on every 10 minutes. The CODESYS will accumulate those statistics, and at the 10-minute marks, we'll just send that information to the Hydro-Quebec. So that's just another example of how flexible CODESYS is and how we integrate it in a generic way where people can just build whatever they want into their application. So that's kind of the goal here on how we implemented the CODESYS. And the configuration that we do is by using the workbench that is built by the CODESYS team. And we build a project, send it to the device, and now it's up and running. So pretty easy to use. So that's kind of the architecture of the SMP gateway support, like I said, RS-232 connection, TCP/IP, and many other functions. So that's kind of the basic. So now, as far as what is the typical use case. So I did discuss about the wind farm statistics on what we do. We accumulate value on the device itself, and then every 10 minutes or every X minutes, we can send them to the person that requires, or the utilities that require to receive those values, and just use them to calculate what would be, for example, the forecast for the power generation, or what's the wind right now, how many do I need to slow down a little bit the pace of production, or so if there's any decision that need to be taken, it's good for them to know these information in advance. So that's what CODESYS can provide to them, that kind of statistics. Also, another one is a nuclear plant state machine. I don't have any screen right now, but this is a type of use case where we implement a state machine, and it's basically the same as was I explained earlier, where you receive different status from the field, and you take decision based on the status on opening a breaker, a certain breaker, to just make sure that you're operating correctly. So it's really just receiving inputs, defining those algorithms. Okay, I'm going to open or close this breaker to allow this power to flow to this transformer or whatever. So that's kind of the way it's implemented for a nuclear plant, and that's one example. The other one, the big controller integration with the protection key scheme, is another application that has been done in Puerto Rico, where it's really, I think it was a drug company, or it's called AbbVie, where they were able to just automate different piece of hardware. So another example is where we use the SMP gateway to just concentrate all the information into one device of what we call a bay controller. So a bay controller is really where we concentrate information coming from different devices, and we can decide if the CODESYS can decide if he's going to operate through one protection or the other. So that's what we did in this project, is concentrate information based on this, send the control to this protection A or protection B, and decide if which one should do it. If it fail on one protection, we can send it to the other. So all the CODESYS engine was able to take those decisions and send the correct information. And based on the result of one command, it can send back to the other protection and make sure that the command is sent correctly. The other one is a VFI project, and that's exactly what's Reza was about to present. I don't know if he's there, or if you can see Chris, if Reza is now in the room, or
yes, I'm there.
Oh, great, Reza, thanks for joining. So
No,
are you ready, Reza? Can you
yes,
okay,
yes.
so if
you want me to share my screen?
No, just tell me when to change the slide. I can do that. If you want, you can present yourself and just go ahead.
Okay, sure. Hello, everyone. Reza Degan. I've been 22 years in the industry, 10 years with EATON substation automation team, basically working on SMP Gateway and some other software products. And I just accepted, I moved to a new position as a utility solution architect for the sales team. So this project that I'm going to represent today is basically, it was a use case for using CODESYS in SMP Gateway. We'll talk about it a little bit more. Francois, can you go to the second page? The next page, actually. Yeah, next. Okay, so the story goes like our EATON's transformer team, they approached us. They were looking for a solution. First of all, embedded solution, something that doesn't need a PC especially an industrial PC, because the way they are going to use it is outdoor on the transformer pads. There is no control room. There's nothing that you can put a server over there. But they were looking for a solution that is not just a one-time solution, like a project-based thing. They were looking for something with minimum code modification and something that they can reuse in the future with just a minimum changes in the setting, and they can use it for other projects or other installations. So next page. Yeah, the whole idea is they have some relays that control some transformers. So you're going to have a number of transformers in a line that is fed from two different sides. And the whole idea is once a relay detects a fault somewhere, generally the protection system, it starts to isolating the fault. But the one after that, they were looking for a restoration system that can check the system and to find what is the best way to rearrange the whole configuration of the system, to rearrange, open and close the breakers, so we can feed the maximum number of transformers in the system. So let's say in this case, if you see, let's say if the fault happens on the line between, from the left, between the third and the fourth transformer, once the protection relay isolates the fault, it will open the two breakers on two sides of the fault. And then if you jump to the next page, yeah, basically it isolates the fault. And then I believe there's a next page too. No, going back. Yeah, so if you go back one page again, you will see, yes, you can see that those that green breaker between the second and the third transformer, once the two ones on the sides of the fault, they are open, that one should be closed. So the third transformer, this time it will be fed from the left side instead of right side. Next page. And this is going to be, so that's going to be the whole idea of this restoration. Next page. Yeah, the system function, they were asking for a few different requirements for this code. First of all, the transformers can be set up in multiple branches, maximum 8 transformers per branches. System can work in 2 different modes. In manual mode, logic doesn't execute even if a fault happens. On the automatic side, if something happens, basically it will start looking around to see what would be the best configuration of the switches, and it will do the restoration. And they also asked for another function to put the system on a default configuration, or what we call it, return to normal. So if there's no fault in the system, the user should be able to put the system on a default configuration. Next page. System elements. For the logic engine, we use SMP gateway. Francois already talked about different aspects of SMP gateway. You know, there's a soft PLC engine running on SMP gateway. The communication protocol was IC 61850, basically to get especially the status points and fault status from the relays to SMP gateway. We also used some of the automation function features in SMP gateway. And I don't know if Francois talked about it or not, but automation function is basically, it's another type of logic engine that is generally used for less complex logics. So doing some very, very simple if else type of logic, adding two numbers or checking the status, doing and or stuff like that, they can be done using automation function plus some more functions that are supported inside SMP Gateway. And then we offer two different options based on the two different models that we have with SMP Gateway. The left one, the bigger box, that is SMP 4260 for bigger projects. It supports multiple branches of transformers with a local HMI. Basically, you can connect a screen to the back of the box and you will get the single line diagram on the screen. And for smaller projects, SMP4DP, the smaller box, the one on the right side, that supports only one branch of transformers, up to 8 transformers. And it doesn't have a local HMI, but it still supports a web HMI in the sense that you can remotely connect to the box and see everything on a web interface. The 4260, SMP 4260 option, it supports both of them, local HMI and web HMI. Next page. So for the protection side, we use EATON ETR 5000 transformer protection. What we were doing during the project, it was like a joint operation between us, the substation automation team, transformer team, and also the relay team, that they were doing some design at the same time with the relays. So we always had to communicate between each other, make sure that everything is working on both of the sides of the logic. The protection relay is using Goose communication for fault detection and trip. Basically, the protection system is on Goose, and then the communication between the protection system and SMP Gateway is IEC 61850, basically to exchange values and status of the relays to SMP Gateway. And with ETR 5000, the way it is designed, it can support 2 switches or 2 breakers for 1 transformer. So you can see on the diagram, let's say if you have 5 transformers, you will have 10 breakers and you will have 5 ETR 5000 relays. Next page. Next one, the logic. Yeah, so this is the logic sequence diagram, just the overview of what happens during a fault. So on the left side, we have the protection relay. On the right side, we have the SMP Gateway. When protection relay detects a fault, first of all, it trips the relay and it sends something that we call protection done. This basically says to SMP Gateway that everything is okay, the fault has been isolated. And then SMP Gateway starts to execute its logic, and it sends all the open commands to the relays. It waits for the confirmation of all those commands from the relay. Once it's sure, it makes sure that all the breakers that are supposed to be open, they're open. It sends the close commands. It resets at the end. Once it's everything is okay, it resets. Actually, this diagram, I think I'm missing something here, because I know why, because this is something that we changed almost at the end of the project. At the beginning, we were not waiting for the confirmation of close commands, but we run into some problems. So we had to add this confirmation of the close commands too. Anyway, after sending the close commands, the way the logic works right now is it waits for the confirmation of the close commands, and then it resets the protection done. Basically, it tells the protection system that everything is done. We are ready for the next fault. Next page. Okay. Yeah, the concept of protection done. One simple way to do this is to start the logic once a faulty breaker is detected. But there are some problems with the system. What if the second breaker is not tripped yet? how do we know that the protection system has done everything that is necessary to isolate the file? We can wait for, one solution would be to wait for 2 adjacent faults. But what if there are more faults? How do we know if there was 3 trips, 4 trips, 2 faults at the same time on the system? What if there's only 1 fault? And this can happen when there is under or over voltage faults on the first and the last breaker. So the idea of using protection done concept is to wait until the protection system finishes its job. And each ETR 5000 has a protection done bit. One or some relays will raise their bit when the protection is done. So as long as we see one protection done bit in the system, we know that everything is done. Protection has isolated the fault, and now it's time for SMP gateway to start its logic. Next page. So here's the general logic for the restoration. We wait for the protection done signal. We logically open all breakers. And by logically, it means we don't send any commands. We just internally, we have some bits for each of the breakers, and we put them at 0. And then we start swiping from left to right. And logically, again, we close each breaker, if not faulty, until the first faulty breaker reaches. So this is swiping from the left side, we stop, and then we start from the right side. Again, we swipe from right to left, and logical close all the breakers until we see a faulty breaker. For all the breakers, once after step 4, we know which breakers should be open or closed. So the last step would be for all breakers to send to basically to match the physical status of the breaker with the logical status. So we'll send a physical command if logical status is different from the physical status. Next page. Yeah, here is, we'll just talk about why we decided to do first logic, then physical. And obviously it's because we are trying to avoid unnecessary mechanical open and close operations on the breakers. So when we use logical and then we match it with the physical, we only open close the relays that have to change the status. Next. Yeah, selective goose setting, that was another thing. This one basically, it was asked by the protection system designer. So they use this protection, they use to detect, these beats are used to detect the communication failure between the relays in the system. System is designed for 8 relays, but there are some cases that you may use less than 8 relays in your system. So there should be a way to tell the protection relay that some of the relays are not there. So it's not because there's a COM failure, it's just that those relays, they don't exist. Each relay has 8 flags. This is the way SMP gateway logic will program the protection relay. So for each relay, we have 8 flags, 1 for itself and 7 for the rest of the relays. And each relay turns off its index and all the indices for not existing relays. Flags are set during the initialization. And just an example of this, we see we have 5 relays instead of 8. So the relay 6, 7, and 8 are missing. Just an example, if you see on R1, the first relay, we set 1 for that relay, and we also set 6, 7, and 8. So basically on all the relays, we set 6, 7, and 8, and we also set the index for that specific relay. Next page. Yeah. Block source, that was again another request from the protection system. Again, in the beginning of the logic, SMP gateway should program that part of the protection system too. Relays connected to the source should also monitor under and over voltage conditions. So we have to tell the protection relay which relays are connected to the sources. Basically, we just block that function on the other relays. We only activate them on the breakers or the relays that are monitoring those first and last breakers on the system. Next page. Okay, yeah, the concept of return to normal. In the absence of any faulty relay, users should be able to restore the system to a default arrangement. There is one more, basically, that's just when the system is not faulty, but there is one special case, and it's when a source returns to a normal voltage from under or over voltage. This is, again, this was a request specified by the protection and transformer team. So they wanted only, not for overcurrent cases, but only for under voltage and over voltage faults. If the system, or if the first or last breakers, they are going back to normal voltage, they wanted the logic to automatically try to restore system to a default arrangement. Next page. Yeah, this one is not really important. It's just to say that when we're doing the configuration, we consider it for two main type of relays. For now, we are just going to use ETR, but they are working on another relay, which is called EDR 5000. The only difference is the EDR can control only one breaker. In the future, there's a possibility to use the second configuration, the bottom configuration. Basically, for the connection to the sources, they will use those EDR relays instead of ETR relays. So you can see the difference between the configuration when we use ETR only, or when we use ETR for for the transformer, or inside the branch, and we use ETR for the sources on the left and right side. It's just, it changes a little bit the code, but generally you don't really need to know about the difference between, unless when you do the configuration. Next page. Okay, code structure. So here you see the this IO diagram. We don't really need to go through the details of every communication, just to see just an overall look of how the system works. You see there are some communications between the ETR and the soft PLC on the right side. There are some binary input, binary output points related to each breaker, or the part of the relay that controls the breaker, and there are also some points that are related to the relay. So everything that you see in front of the breaker 1 on the top and breaker 2 on the bottom, those are breaker specific points, and then everything in the middle, those are relay related points. Just an example, we talked about the concept of selective goose or block source. They're all in the middle because they are relay related. We also have two files. We'll talk about them. And if you see at the left side, the yellow boxes, return to normal TXT and configuration TXT, those two files, they are to define the configuration of our logic. And these are the things that once the code is done, we just change the for every new installation, we just need to change those text files to feed the new configuration in the new installation to the code. We don't really need to change the code anymore. And then we have the SMP HMI, and those are basically, these are the points or the controls that SMP Gateway receives from its HMI. So one example would be when a user on the HMI decides to put the system on return to normal mode. This is a command that will be received from the HMI side. Next page. Yeah, this is the functional diagram of the system. So again, not sure if we really need to dig into each of those functions, but you are all familiar with the whole structure of the CODESYS. Basically, we have a PLC main, which is the function that, or the module that begins the process. So that's the initialization phase. And PLC main, it needs to execute some different codes that I already put here. These are different classes that I define in my logic. Some of them are to read information from the text files, initialize the points that we need, and again, to set up the initial status of the relays, exactly what we talked about, stuff like selective goose message or block source points for each of the relays. And once the initialization is done, we just start looping around this ST program. And that ST program, it has different modules to do the, basically to execute return to normal, to execute the automatic restoration, and to loop through the status of the system to see if we received any commands, either from the relays in the form of protection done that triggers their logic for restoration, or in the form of a command from a user through the HMI. So you see all the blue boxes, they are the execution or runtime modules, and everything in green, those are the initialization phase. Next page. Okay. Yeah, the general structure of the variable. So I have two main structures in my system. I have a branch structure and a breaker structure, and we also have the global variable. So the way it works, we have an array of branches. So there are some information inside this branch structure. The most important one is an array of breakers. In fact, it's an array of breaker structure type. And under breaker structure type, or breaker STC, I have all the information related to each of the breakers, stuff like what's the current status of the breaker, if it's faulty or not, what kind of command, or we were talking about that logical command that we send to the breakers before we actually send the physical commands, and of course some of the points that are coming from the relay. Those are the points that we have to send a command on, or we read some information from, and those are the physical points coming from the relay, unlike some of the logical points that we just create inside the CODESYS logic. Next page. Yeah, challenges and solutions. So we run into some different problems and challenges, and we had to work with the protection system, first of all, to figure out how we can solve the problem. Sometimes they needed to change or add something on their side. Sometimes we needed to adapt to what they were asking for. One of the first challenges that I had, I was a little bit confused, was how the relay will receive the command. So every time we want to send an open close command to the relay, well, general way, the easy way is just to send like a binary open command. It could be 0 for open, 1 for close, but it really doesn't accept or we can send a pulse. There are two ways. You can send one binary output, 0 for open, 1 for close, or you can have two separate points, 1 for open, 1 for close, and then you send a pulse on open, it will open the breaker. You send a pulse on the close point, and it will close. But it really doesn't really accept a pulse command. They only react to a rising edge, which was a little bit strange. So we have to, basically they were seeing it, they couldn't receive a pulse. They could only see a switch on that point, on that line, to be close and then open. And it would consider that as a pulse. So we had to simulate this pulse thing with close, wait, and open. That was the way we were sending open close to the relay. So still two separate points, but on each of them we needed to simulate a pulse using close, wait, open. It's not impossible to do this in CODESYS, but we had a more straightforward option using our automation function in SMP Gateway. Because in automation function, we already support a function which is called the command conversion or control conversion. Next page. So yeah, the way it works, and this is a built-in function in SMP Gateway automation function. It gets the command on one binary output that can be a 0 or 1, and then internally it will change the command. It basically creates two separate points, and on each of them it can simulate that the pulse using close, wait, open. And that was exactly, you can see it on a screenshot on the bottom of the page. The input control point is the point that SoftPLC generates. And then we can say, okay, if you want to execute or to use this as an open or close, and what kind of command, it would be a simulated command. And under on time and off time, we just specify the shape of the pulse. So when we say the on time, basically your pulse command would be up for 300 milliseconds. Next page. Closing delay. That was another challenge because making sure the two sources never get parallel is essential to the system. If for any reason we close all the breakers in the branch, that would be disastrous. So that's why we decided to send commands in two passes. So we first send open on the breakers that need to be open. So we just make sure there is another check. There's always another check. Every time we send commands, we check that at least one breaker is open. That's internally. But to send the commands, we always do it. Send the command on the branch, we always do it in two passes. We first send the open commands and we wait for the confirmation. This is just to make sure at least one breaker would be open in the branch, and then we start sending the close commands. How to make sure open commands or an open command was successful. How to make sure the open mechanism is not faulty, because if you send a command and you don't wait for a confirmation, you can never understand if it was okay. And then if you start closing and for some reason the open didn't happen, that could lead to a big explosion. Open commands execution has some delays. That was the source of the problem, because waiting for confirmation, as in many coding, like in C++, for example, you can do something and then wait for a specific time, 1 second, 2 seconds, 3 seconds. This is not possible in CODESYS. CODESYS doesn't support, at least natively doesn't support waiting per se. So next slide. Yeah, so to do this, and then a little bit later, we decided to get the confirmation for close, for open commands and for closed commands, and it led to the concept of, first of all, waiting for enough delay to make sure the breaker is closed or open, and then soft PLC code. As we said, it cannot go on a pause. So we decided to come up with a state machine. And the whole idea of state machine is it sends a command and then it just loops in a waiting loop. So every time it goes back to the condition, it says, okay, what's the status of the, basically in this state machine, I think we have 5 different or 6 different statuses. We have normal, which is there is no command, we are just waiting for something to happen. And then once something happens, let's say if there's a restoration and we are supposed to send some open and close commands, we start sending open commands, and we put the system on open status, in the sense that in the first loop, it just sends the open commands. And once we send the open commands, we put the status of the state of the machine at wait for open. And then it takes you to another loop. It just loops around. And in that loop, 2 things happens. First of all, there is a timer. And it also checks if it receives the confirmations from the breakers. So if at any time it receives the confirmation for all the open commands or all the breakers, they say, yeah, I did my open command, it just gets out of this state and it goes to send close state. Otherwise, if after certain time, because we also start a timer in that loop, if the timer expires, we know that there was a problem in the system because we send open commands and we didn't receive confirmation for some of them, and then it would take you to the state of error that will take care of it takes care of the error. It sends a message, it tells the user that something was wrong, and it never it never starts to send close commands until the user fixes the problem. But again, if all the open commands, if we receive all the confirmations within the timer time, then we put the state of the machine to send close. And again, it's exactly the same as open. It sends the close commands to all the breakers, and then it changes the state of the machine to wait for close. And in this wait for close, again, we trigger a timer, we wait for the confirmation, and if all the commands are closed, we'll go back to the normal state. Next. Yeah. Another thing that was asked by the transformer team was the ability to have on the HMI single line diagram, the ability to have lines that are energized or not energized on different colors. The logic to decide which line should be red or green can be implemented in automation function, but it's not flexible. Again, as I said, with automation function, first of all, it's not flexible and it's much more complex. With CODESYS, CODESYS can verify the path from each source to a certain breaker. So if a breaker is closed and all previous breakers are closed and active. Basically, if there is an active path from a source to a breaker, that breaker is marked as active. And then for each section of the line, if the two breakers on two sides, they're active, it means that section is active too. So that's the way, basically we generate a list of points or an is energized attribute for each section of the singular diagram. Could be a breaker, it could be a section. No, sorry, it's not for a section, it's only for the breakers. And then in the HMI, because even in the HMI, we can put some simple logics. In the HMI, we'll say if the right breaker and the left breaker, they're both closed, show this in red. Or if at least one of the breakers on two sides is, and if both of the breakers on two, again, if one breaker on one of the sides is closed, turn it to red. It means that the line is energized. And if both of the breakers on the two sides of the section are both open, then show it in green, meaning that the line is not active or is not energized. Next. Yeah, system configuration. So going back to the requirements that I mentioned in the beginning, one of the most important ones was they were asking for a product, in the sense that we just code, we create the code, create the product. From that point on, you don't really need to touch the code anymore. All you need to do is to feed the configuration of the new installation, and the code should be able to read this configuration and adapt based on what it reads from the system. So basically, the way you feed information or the configuration information to your code is through those two text files, pointlist.txt and return to normal.txt. The point list, first of all, it tells how many branches and how many breakers you have in the system. And then it tells the code for each of the breakers, what are the points that it needs to read from the relays. Like what is the name of the point for the status? What is the name of the point for a fault or something like that? And the second text file, which is return to normal, it's just the status of each breaker when we want it to be in the normal configuration. So it's just a bunch of 1 and 0 numbers in the text file. And then it was not necessary, but I found it useful to, instead of, because these text files, as long as you know the structure of the text file that is supposed to be fed to the code, you can do it manually just using a notepad. But I decided to create a spreadsheet using macros. So using that config generator, basically you just need to say, okay, I have I have 2 branches, and in each branch I have that many number of transformers, and then you just put the name of the points for status or for fault. And once everything is okay, when you hit execute on that macro, the macro also generate all the necessary automation functions, and it also creates the point list.txt and return to normal.txt. So it makes it more error resistant, and it speeds up the process of configuration. And to feed the code to SMP Gateway, well, one way would be always to use the CODESYS workbench, but because this one is a final product, you don't really need to change the code. What we do is we just create a package file, and once we push this package file to SMP Gateway, basically it's just the code. Once we push this package file to SMP Gateway, it will extract the package file, which is a kind of zip file, and it puts the elements of a soft PLC at the right place so the code can be executed. And then at the end, there is another file too, which is our file for the HMI. And this is the file that SMP Gateway uses to show the single line diagram, either on a web interface, or if we go with SG4260 for the local HMI with a screen to the back of the box. Next. Yeah, this is just the idea of that spreadsheet with macro. On the left side, these are the information that I feed to the Excel sheet. On the right side are the things that I get from that macro. So on the left side, I just say what's the number of the branches. System configuration is another thing that I have to specify, if it's using ETR only relays or EDR. As I said, EDR is not, for now, it's not necessary, but we just made it so it's future proof. And then IEC 61850 protocol instance prefixes. These are some stuff in SMP Gateway. And then finally, the point names in each instance. And on the right side, the macro will generate the point list file, the return to normal file, and it also generates automation function points and automation function functions that I will need in my SMP Gateway. Next. Yeah, just some lesson learned for me, because I was kind of new to CODESYS. I had worked with CODESYS before, but I never implemented a full project using CODESYS. So there were a lot for me to learn. One of them, which is very useful, most probably you already know about it, but it's the compare function in CODESYS. And the reason for that is the guy in the transformer team, he had to set up a private network for him to be able to test the system. So I couldn't reach that network through our corporate VPN. So every time I had to send the file to him after each modification, and it was not right from the beginning. It was almost at the end of the project when we were testing. But every time there was some issues during the testing, I had to modify the code. And then just to make sure that we are all on both sides, we are using the same version. Every time I was sending the modified version, he was using this compare function to make sure all the modifications are taken affected in his code or in his machine. Next page. Yeah, and just some general programming tips. Again, I'm pretty sure you already know that. Always comment the lines. It's very important, especially I was the only person who was working on the code. But because of some delays, we're waiting for some stuff from the transformer team or from the relay team. So sometimes I wasn't working on the code for like a month. And then when I was back, that was the comments that were helping me to exactly understand where I was and why I put that line. It really helped me to better understand the whole logic of the system. Using structures and enums, these are the things that, again, it's coming back from the object-oriented concept. It really makes it easier and makes the code more understandable. Yeah, that was another thing that I didn't know, that soft PLC doesn't support dynamic allocation. So unlike like C++, that you can create an array and assign the memory space at the runtime, it's not possible in soft PLC. You have to, before you start to run the system, you have to say what's the size of your array. Global variables, a good way to pass parameters between the functions. Yeah, this is something more SMP gateway related. So subscribing RTDX, because in SMP gateway, the traditional way is once you have to subscribe to some of the points in SMP gateway, and then we will import those points through an XML file into CODESYS. But if you already know what's the name of the point in the RTDX, you don't really need to define it. You can define it during the runtime. And another function that is supported in SMP Gateway, it's a function called SMP log. And because in SMP Gateway, we have an application, one of the tools that we have, it's called SMP log. And SMP Gateway logs almost everything that happens inside it. And then through that, you can go through different categories like security or firewall or protocol logs or startup logs. And using SMP log, you can write to those logs. So I was using it a lot for debugging. It was telling me exactly if my code was crashing, if it was not working as it was supposed to. Going back to SMP log, finding the hints that I was putting in the log using this SMP log function, it helped me a lot to faster debug the code. And then the last one was the idea of generating a package file. So there are two reasons you may want to do that. One of them is, well, if the code is not really needed to be changed, your client or your user doesn't need to install CODESYS again. You can just give them the package file and it will work on the SMP gateway. And the second case is just in cases if you want to protect the the code that you write for some different reasons, copyright thing. Again, we can just deliver the machine code, the package file, instead of delivering the whole program. And I think that's it.